previously used to be considered to be difficult, hard kind of problems. They become not hard anymore. Some problems that are very complex. So if you have a very complex interactive type system, these can become simple using the FRP metaphor. And due to its basis in functional programming, as opposed to being monolithic programs, so that's the most common case would be like a game, a very monolithic type thing. These become modular. So you end up with a lot of tiny reusable pieces that build up your program, and then you can reuse these in other programs that you make. Okay, and this is also based in math. So how many of you guys think that because something is based in math, it becomes more interesting? Raise your hand. Okay, about like 25%. That's about what I expected. Okay, cool. So before I jump into it, I want to recap what denotational semantics-based design is all about. And denotational semantics, that is really hard to pronounce, but it's not a hard thing to grasp. What we're trying to do is we're trying to understand the mental model of our user, right? Or the mental model of the problem at hand. And based on that mental model, we do our design. So as a good example of this, we have iterator vocabulary, right? So this vocabulary was created, and it's based on the idea of contiguous memory with pointers to the beginning and end of a contiguous memory, okay? Now, that works perfectly for arrays because that's exactly what it is. But like a standard list, you can think about it using iterators as a contiguous place in memory with pointers to the beginning and the end, right? So that's the mental model of iterators. And here we have this kind of a loop, and that's wonderful. But we've seen a kind of transition in our vocabulary for doing this kind of thing. Now we have this, right? And the mental model of this thing, so semantically, this is the same as the previous slide. What we're doing is we're taking iterators from the beginning and the end. We have the contiguous place in memory, and we move those pointers. So I don't think that people think about that when they see this code, right? I argue that when people see this code, they think about something like a bag full of stuff. You take one out, you do something with it, you put it back in, and you grab the next thing in the bag and do something with that. And actually, I'd even go further, and I'd say that for a long time, people had that kind of bag mental model even when they wrote this code. Like, how many of you guys have wrote code like this a million times? Yeah, everybody. It's not. I don't even think about it anymore when I write code like this. It's just like brrr. So this is what is on my screen, but what's in my mind is this. So this was an advance, in my opinion, because the syntax has gotten closer to the mental model that I had in my brain, or that many others had in their brain. And this is much more approachable. Of course, you get into the details and you have to know about the iterators, but I think this is a big improvement. So what we want to do is we want to figure out what the mental model is for interactivity itself. And the way that we're going to do this is we're going to look at some example programs and try to construct that. Just describe what it is that you see. So here's our first example. Let's see if this works. Well, put it on the wrong screen. Okay, so here's a program. What do you see? Raise your hand if you can describe what you see on the screen here.
There's a red dot.
There's a red dot. Okay. Does anybody want to refine that a little bit? No?
It's centered.
It's centered, right?
And static.
And static, right? So what do you mean by static?
It doesn't move.
It's not moving, right?
When I first saw that image, I thought, well, that's gonna be a bouncy ball thing, and it's not moving.
You're right. Yeah, it's not moving. It has a location. It's in the center of the screen. Does anybody else have anything else? Any other way to describe this?
There's a line.
There's a line going across. What is that line? Is that part of this thing?
Yeah.
Okay. That's a bug in the projector screen.
I would call it a circle, not a dot. But
Oh, okay. I hear, someone said that it's called a circle, not a dot.
There's a mouse pointer.
There's a mouse pointer. Get that thing off of there.
Bad example of a flag of Japan.
All right.
Black outline too.
Black outline? Yeah. Okay. I didn't hear anybody say that there's a clump of pixels in the center of this thing. Right? And
Pixels all over it.
what's that?
Pixels all over it.
Well, yeah, it was too late. Now that I brought up pixels, you can't start saying pixels. Everybody talked about a dot in the center of the screen, right? That's the mental model we have when we look at this thing, not a clump of pixels. All right. Let's do another one. All right. Now what do you guys see?
Clump of pixels. Did I get it right?
A clump of pixels. No, that's wrong. No, there's no wrong answer. So,
The weird thing to me is that not only is the circle going around, the circle is actually rotating itself as well. Like I don't think it's sliding. I think it's rotating. Like the difference between my hand doing this and my hand doing that.
okay, so somebody sees that, Tony says that it's rotating circularly like this.
but it's symmetric. There's no way you can tell.
No, exactly. But I still think of it that way.
Oh, yeah.
Mm-hmm.
I don't feel it's sliding around.
Okay, so
I do.
so I heard the word sliding, circling,
Rotating.
rotating, orbiting. But I didn't hear anybody say this is like a set of frames, and in each frame that this thing is redrawn with a circle in a new position. I didn't hear that. Right? So, so we're learning a little bit in terms of what's the mental model that we have when we think about this kind of thing. All right? All right, let's do one more example here. What is this?
Stalker.
Common as stalker, yeah. What does a stalker do?
It's interactive.
What?
Follows the mouse.
A stalker follows the mouse.
So it's a cat.
Okay. So we have a ball here, right? I mean, we say that it follows the mouse, or it's at the mouse. Now, what is the mouse cursor? How can we describe that?
Pixels.
Okay, I heard the comment pixels.
The result of some event and
Okay.
Your hand.
What's that?
It's your hand.
Okay, I heard it's your hand.
interaction point.
I heard an interaction point. Okay, so the mouse, how can you describe, I mean, does it make sense to describe its position? What is its position? How would you say?
Wherever the dot is.
Okay, wherever the dot is. Could you say that the mouse position is a string of characters? Does that make sense? Not so much. I heard XY, right? But I would say that the XY doesn't really describe the mouse position completely.
Well, XYT.
I heard XYT. What do you mean by XYT?
So you have to not just specify the Cartesian coordinates, but the time as well, since it's moving in time.
Okay, so we have the idea that it's an X, Y, T. All right, is that sufficient to describe what the mouse position is? Is everybody happy with that? So what would this be then? Like 4, 5, like, time 1.0 or something like that? Okay. So that to me describes the mouse position at a particular point in time. But that doesn't describe the mouse position over here, because here time's changing. So maybe we would have to have a list of these, right? So how many of these would be in the list? Infinite.
Well, whatever the resolution of the
Stream of
computer is,
XY
but
points.
Okay. So I have, someone mentioned a stream of XY points. So now we have 4, 5, another position, maybe 4, 6, some kind of infinite stream. But what about in between these 2 points? Can't we also have a mouse position in between these 2 specific points? I would argue that at every point in time, we have a mouse position.
which makes it a function.
Which makes it a function. Yeah, so we have our time as the domain of the function and our 2D point as the codomain. That right there is the basis of functional reactive programming. A function from time to point 2D. Or, this is the mathematical notation for the type. We can just think of it like this. A boost function or a stood function that takes in a time and returns a point 2D. All right, great. Now we have the proper semantics. How do we implement this function? Any ideas? Well, it's not easy to implement this function, right? If we could implement this function, this would be extremely useful. Because I could just say, pass in time tomorrow, and where's my mouse position, and I can decide, based on what I'm going to look at tomorrow, how much I enjoyed it and whether or not I should look at it. Or go into yesterday. So we could probably implement something like this that accepts all time before the current time, right? Then what would be the problem with that? Or caching, memory, right? I mean, if you do that, then you're going to build up this gigantic structure, and you're going to run out of memory, right?
You said there's an infinite amount of time. It's continuous in time, so you can't ever cache it.
So the comment is that it's continuous in time. You can't ever cache it. Practically speaking, though, the computer can't. The computer only knows individual points, right? And we can connect those with lines. So it's not necessarily something that a computer can't represent, right? We can always interpolate between 2 points. But the idea is, if we go backwards in time, then we got a caching issue. If we go forwards in time, then we got a time leak, right? It'll basically have to pause and wait for that to happen.
But it is ignoring certain aspects of the computer, right? It's discrete time. It isn't continuous time. And so pretending like you knew what happened between the 2 discrete points is...
That's
Right.
actually what you end up doing, though.
It is what we're doing, but I'm just trying to be basic about the math.
Yeah.
Mm-hmm.
It's not what the math is stating.
But he's pretending.
So the comment is that when you actually get down to implement this thing, we only have discrete points. We can interpolate them, but we don't really know what happened in between those points, right? I could just be sitting here moving my mouse and then just jam it over here real fast, and it doesn't even notice, right? So it would be an incorrect representation of what happened in reality, or an approximation which is not really close to the reality.
There's any number of functions that fit those points.
Yep, the comment is there's any number of functions that fit those points. Yes. Saw a hand up over here.
I think that Michael's comment means that we don't need infinite storage to capture the past. We only need from the time it started and a discrete. So it's finite, but very large.
Yeah, so the comment was that we don't need infinite storage. Maybe it's the time that you boot up your computer until it gets trashed. So it's very large, but not necessarily infinite. That's true.
Does it not just depend upon the domain of the usage?
So the comment was, does it not just depend on the domain of the usage? Right? It's a great question. And I think that in order for this kind of thing to work, you have to know how it's going to be used. Right? that can help you get rid of the gigantic space leak, which happens in the past, or the time leak, which for values in the future. You have to think about those issues, yeah.
What if the pointer never moves? You turn on your computer, just leave it there.
So the comment is,
Goes by, but the position is static.
so the comment is you just turn on your computer, the pointer just stays there. You can probably come up with some kind of compression and fix your memory problems, or somewhat anyway. But anyway, these are sort of beside the point. Let's just assume that we have this implemented, just through some magic means. And let's try to implement that function where the circle follows the mouse, using this semantic language. So we have a function. It takes in this magical mouse position function. It takes in a point in time, and it returns a drawing that corresponds to that point in time. So presumably we have a circle at function which returns a drawing. It takes in a 2D point and will return a circle at that position. So does this make sense for everybody right here? Pretty simple. So it would be really nice if we could have a magic function like that. Well, we'll take this one step further. And instead of returning a drawing, we're going to return another function of time that returns the drawing at a particular point in time. So we take in our mouse position, which is that magic function, and we're constructing another magic function based on that using a lambda here. So this isn't too tough of a transformation. You can do this with any function, actually. So we capture the mouse position. The new lambda needs to take in a time t, the new function that we're returning, and it'll just return the circle at the mouse position at that time. So do you guys think that this would be correct? Assuming that we had that magic function, would this properly describe the program where the circle follows the mouse? I hear yes. Yeah, I think so too. So we see a commonality here with the argument. So we have this mouse position, which is our function of time, and we have our result, which is a function of time. And we also had this over here, remember? We're talking about this time functions. So maybe we should make this an abstract data type, this idea of a function of time. And we will. We'll call this behavior. A behavior is a function from time to some type t for some, period. A function from time to some type t. So here we use this using expression to say that behavior is equal to a function of time. Now, we don't actually implement it like this. This is our mental model. The implementation is different. But we don't have to think about the implementation when we're working with these programs. We can just assume that it's like this. So a behavior of int is pretty much like a function that takes in time and returns an int. A behavior of a drawing is pretty much like a function which takes in a time and returns a drawing. This is the basic idea of functional reactive programming. A function from time to t. Yes?
So in functional reactive programming, is the int not persistent?
So the question is, in functional reactive programming, is the int not persistent? So I guess I'd flip that around. If you have a normal function which takes in an int and returns a char, is the int persistent?
Yes.
Yes. Okay. So whatever applies to a function would apply to this. But as this is functional, we're talking about pure functions. So given this, we can already make some handy utilities. Here's a function called always. It takes in a value of any given type t and will return a behavior of that type t. So does anybody know, can anybody describe to me what this does?
It's an identity function, or it returns an identity function. It's the functor for a certain monad.
So the comment was that it's an identity function? Nope.
It returns an identity.
It returns an identity function. Nope.
No, it's just constant.
It just returns a constant for all time. Something that never changes. This,
That makes it the injection or the return function for the behavior monad.
Behaviors aren't monads, by the way. No.
They probably don't but it's like a behavior of t, and basically if you do this, it's always, and then you have behavior that always is t. So it's, behaviors aren't monads. They probably don't follow the laws. They don't define. Should I define? But they probably don't follow the laws, but it's like that.
So the comment is it's like a monad. So I guess in the sense that we take a normal value and we shove it in the thing, this is that function, right? And we call it always because it means that for any time t, it's always going to be this particular value. So remember that first example that we had up, just a plain dot in the screen. That would be always the dot in the center of the screen. All right?
Are they at least applicable?
The question is, are there at least applicables? This kind of relates to that. So we have a function called map. It takes in a function, a normal function with arguments and a result value, and it takes in a bunch of behaviors. And it will create a behavior that is a behavior of the return value of that function. So can someone describe to me what this probably does?
It returns a function that takes a time. It takes that time, passes it into all the behaviors, gets the results, calls the function with that, and returns the result.
Yeah, so the comment is that it's going to somehow use this function, apply it to the insides of these behaviors, making a new behavior. So yeah, that's true. And sort of as a side note for those of you who are enjoying this category theory stuff, the fact that this map takes in a function with multiple arguments means that this is not just a functor, it's an applicative functor. That's like the fundamental difference. So that's a side point. Don't worry about that if you don't understand. All right, next piece. Let's look at an example of using this map. So at the top here we have this function called draw over. It just takes two drawings and it produces a drawing with the top on top and the bottom. We have some top behavior which is defined as some crazy drawing, a bottom behavior, and then but remember that these behaviors are drawings for every point in time. So down here, we can combine these two with this map function. So we're mapping the draw over with the top behavior on the bottom behavior. So at every point in time, that drawing on the top behavior is going to be on top of the bottom behavior's drawing. That's what the combined behavior is. So we're putting these things together. So now that we have that, let's revisit our circle follows mouse function. So the first thing that we can do is replace these functions of time with our new behavior data type, right? That's pretty straightforward. What else can we do? Does anybody have any idea as to how we can use map here?
Just map circle apt to mouse pulse behavior.
So the comment is to do this. This is pretty simple, I think. Now, let's go ahead and look at another example here. Okay, so actually this is a new example. This is the same one that we had before. This is just the spinning ball example. Now we'll see if we can program this thing. So what can we do with this function? Is this going to need the mouse position in it? I see people shaking their heads. No. Okay. So we got rid of the mouse position. And let's separate out the idea of the map, because we're going to eventually map the point at to something. So we have the spinning point behavior, and we're just going to use map to make sure that a circle is at the spinning point. But now we need to define the spinning point. So how do we do this? Any ideas?
Well, I would say we imagine a circle. We take an angle based on the time and say use sine or whatever trigonometry.
Okay.
Create functions to say, well, this is the actual coordinate at this point in time along the circle.
Okay, so the comment is to use trigonometry to define the actual point at time that it ought to be. Okay, so here we have our spinning point, just moved it over here. Now we have it as a function of time. So what are the particular things that would go in here?
Circle radius.
X and Y. Well, you would do, first of all, I'd do it in polar coordinates to make it easier.
Okay,
So you would have a radius and you would have an angle, and you would also only have to keep track of time mod orbital period. And then basically I would parameterize theta as to be linear in time. And there you go.
so the comment is to use polar coordinates, and that's a really good idea. It's not one that I had. So let's see if we can do it in Euclidean coordinates.
So just do the transform.
It's our sine theta and our cosine theta.
Our sine theta, our cosine theta.
With time, you have to map time to theta.
Okay, let's say time is in seconds. We want it to go around 1 second, and our radius is 50. So
Well, r is 50. Time is 2 pi in 1 second. So multiply that out, you've got it.
yeah, something like this, right? Does cosine come before sine?
Depends
Where
on
you
where you want to
start.
start the circle.
Right,
Start here or here.
right. So it doesn't really matter for us, right? Because we just see it as a spinning circle. I mean, I guess we could specify exactly, like when you start the application.
One will make it go clockwise, one will make it go counterclockwise.
Oh, the comment is one makes it go clockwise, one makes it go counterclockwise. I didn't think about that. That's a interesting observation. So we take this and we put it all together. And now we have this spinning ball program. And we're going to come back to this in a minute. Has everybody got this? Ready to go to the next slide here? All right. So we can make some composition operations out of this map function, like plus and minus. So can someone describe to me what plus and minus means for behaviors?
Do they commute behaviors?
So the question is, do they commute behaviors?
So, in other words, you chose plus and minus.
Mm-hmm.
I would expect algebraically that they commute in this case.
So the comment is that with plus and minus, you would expect behaviors to commute. And yeah, they do.
You can add or subtract behaviors from a composite.
So the comment is you can add or subtract behaviors from a composite. Well, let's say, let's just even be more simple than that, right? Let's say we have two behavior doubles. What could it mean to add those together? So the comment was to add the doubles. Yeah. So if you have two doubles, two double behaviors, you know they're functions of time. And this one's, can you guys see this? This one's like this. This one's like that. Then we add these two together, and then we'll get this one just up a little bit higher. Right, we're just adding the values at each point in time. There's nothing really special about this.
So it's basically map plus over those two behaviors.
So the comment is basically map plus over the two behaviors, and that's correct. Yeah.
But I'm confused. I mean, just because you can add two doubles doesn't mean it's the right thing to do. For example, if your doubles were r and theta, adding them makes no sense physically, at least.
So the comment is that it doesn't always make sense to add doubles. Sure, I'd agree with that.
Which means, in that case, don't use the plus operator in that case.
Right.
In your code.
So the comment is that then don't use the plus operator in that point. And I'd agree with that.
So just for my own clarification,
Mhm.
I'm probably the last on board here to catch up with. So when we're releasing the plus and minus operator here for behavior, we're really talking about plus and minus for the what it's behavior for, the T, right? Like that needs to have these operators ultimately defined.
So this T template parameter is going to have to support plus and minus. Yeah. So this is just to give you a hint in terms of the composability of these things. So these are by nature, behaviors of T are just going to be just as composable as T's, because you can always apply any kind of operation on the inside of it. And they don't always have to be the same type. You know, if you have a function which takes in different types, it'll work just the same with behaviors of different types. So let's take our spinning ball and pull it out of that function. That wasn't really necessary at all. We just have these top-level definitions. So we have this idea of a spinning point. We have this idea of a spinning ball. I'd argue that these things map to conceptually what we think about these. I mean, is this really a spinning ball? I mean, it's not really spinning. It's just sort of like a declaration in code somewhere. You know, and then we don't even have a way to visualize a spinning point. Not directly. We'd have to convert it into a spinning ball first. So it's kind of neat. These are kind of like integers, you know, when you have an integer defined in your program. It just has its meaning. You know, you can't really do anything with an integer by itself. Let's look at another behavior. So what do you guys think that this behavior is going to do? So we're reusing the things in the previous slide. So I heard the comment is going to spin around the mouse. Let's see.
Assuming, of course, plus for point is implemented as offsetting the point.
Yes. So yeah, we got this thing spinning around the mouse. Now think about how you would implement that without thinking about functional reactive programming. You're using a non-functional reactive programming library. How would you implement that? Think of all the state that's involved. Think about the frame rates. You know, you got to make sure that this is always around the pointer at a particular rotation. That needs to be kept track of. Need to count how long has persisted, how much time has persisted between your frames to make sure you get the movement right. So in my opinion, I think that this functional reactive programming concept has really nailed the semantic domain. I think that writing programs like this in the way that we just did is so much easier than the alternative. Yeah.
I still feel like I'm waiting for it to get real. Like, how do you wire a function of time to a UI like this?
So the comment is, how do you wire a function of time into a UI like this? And I'm sorry to say that the last third of the talk is going to be about that. So we're going to have to hold our breath a little bit. But it'll work. It'll all come together. All right. So that ends our introduction to functional reactive programming. So we take a little pause. And what I'm hoping you walk away from this little basic tutorial is just how composable these things are and how easy it would be to program if we had something like this. So there's a question over here.
Your comment about keeping state for the non-FLP style.
Mm-hmm.
Even in FLP style, you still need to, when you get down to it, be careful about numerical stability of that calculation of time, right? You still need to.
So the comment is that we have to think about numerical stability in that function of time. Yeah, but that's no different than the rest, any kind of programming, really. Yeah. All right. So now I want to, take a step back, because we've just learned about functional reactive programming, not necessarily my library. I mean, anything can do that. And take a look at the history of functional reactive programming. So these guys, Connell Elliott, Paul Hudak, 1997, wrote a paper about this thing called Fran. And they invented the semantics of functional reactive programming. This was Haskell. All this is Haskell. they went and made this other paper called Genuinely Functional User Interfaces, where they refactored it a little bit. They changed the semantics that you actually use a bit for some performance reasons. We had functional reactive programming continued, where they made this library called Yampa, which is really probably the most stable functional reactive programming library in the Haskell world. We have the Yampa Arcade, where they actually used functional reactive programming to make this arcade-like game, because people weren't quite sure that you could actually use it for something real. And then finally in 2009, Connell Elliott wanted to go expand the theory behind functional reactive programming, I guess I'll put it like that. And he made this library called Reactive. And one of my contracts that I was working on, I was actually working on that Haskell library. Now, you would think that anytime someone mentions Haskell, they would just shout out about how awesome functional reactive programming is. But they don't. And the reason is because there's been a lot of implementation problems with functional reactive programming. Poor and often unpredictable consumption of space. One of the papers I just mentioned used that exact wording. Lacking dynamic collection capabilities. The subtle implementations with regard to laziness. And it's complex to use these with imperative libraries. You know, because the mismatch between a purely functional language and a purely imperative language is difficult. So I would argue that these are not problems with functional reactive programming. They aren't challenges that are inherent to functional reactive programming. I would argue that these are Haskell problems. And for those of you who have been in the Haskell world, you've seen these things, right? You know that these are true. So how can we solve these problems? Anybody have a good idea?
Well, don't use Haskell.
Don't use Haskell? Okay. So what should we use then?
Java.
What's that?
An engineer.
An engineer? Okay.
That's what engineers do, right? I mean, they solve engineering problems.
So what language should we implement this in? Come on, guys.
Just not gonna give it to us.
Use C++. Well, so someone already did that. And the subtle space leaks and the dynamic collections awkwardness still remained. Oh, crap. And what they did is they just took the Haskell implementation and they just transferred it over to C++ directly, sort of like Bartosz did yesterday. And they ported over a lot of the problems.
Similar results as Bartosz got.
You got similar results that Bartosz got, yeah. So, well, I mean, I don't think there was a performance difference in that case. It was just the problems remained, all right? So, all right, so we've already had an implementation in C++. So,
Is where we use an engineer.
so this is where I get into this. So here I am in 2011 with my intern, Elliot Stern. Well, okay, this is not a real picture, right? Elliot Stern was much older. That's actually my son posing for the photograph here. The thing that's real about this is the semantics. So I was working on the semantics for a contract I had to make a 5D CAD/CAM application for a very complicated robot. And I'm out here working on the semantics. And this is what happened when I realized that the semantics that I came up with were the same as the semantics for FRP. Crap! Because I had already done the FRP thing in Haskell, and I knew all these problems that were there. So I was just pretty upset about this, because if the semantics implied a FRP implementation, and I knew all the problems that were there, I was just like, man, what am I going to do? So what I decided to do was to just ignore the problem, as I like to do that sometimes, right? It's a really huge problem. You don't know how to solve it. Let me just pretend that doesn't exist and move forward. And that's what SFRP is. I didn't look at the Haskell implementation. I derived the semantics directly in the C++ using the C++ idioms, the C++ way of doing things. And that is where SFRP is unique from all the other C++ implementations so far, is that I derived everything directly into C++. Now, this actually solved a lot of the problems. And the ways that things were done in Haskell, I did them in a different way in C++ that would make more sense if you're writing a C++ library. And also being ignorant of the Haskell stuff, because I just put that out of my mind, was a big help. So one of the issues that were solved was this idea of a wormhole. So I'm going to show you an example here. So here we have another program, and when I move my mouse in the edge of that circle, it grows a little bit. So if we wanted to implement something like this, let's say we have an in-circle behavior, which just says true or false as to whether or not you're within this circle. And we have a circle radius behavior. The problem that we have is that whether or not you're in the circle depends on what the radius is. And what the radius is depends on whether or not you're in the circle, right? Or whether you're transitioning from into the circle. So we have these two names that depend on each other. And in Haskell, that's not a problem, right? You can refer to names, one before the other, doesn't matter the declaration order. But in C++ you can't. So what I did is I made this wormhole idea. And this is just a synopsis of it. You create a wormhole. Well, this is the synopsis. You can ignore it. Let's look at the usage. So you create a wormhole. So this is an int wormhole. You give it an initial value, and we'll understand why it needs one in a second here. And you can use hole.output behavior. So before this wormhole is completely defined, you can make use of the behavior. And then our final behavior, we can set the input behavior of the wormhole. So that's why it's kind of like a wormhole. You have this behavior which is defined way down here. You have another one which is up here. You want to get access to that one. You do so using a wormhole. That's what this construct does for you. So to look at this example, the growing the circle with the wormhole, I create a circle radius wormhole with the initial value of 10. And then my in-circle function can make use of that wormhole. So we're mapping this function here. This just says, given a position and a radius to see whether or not the position is within the circle defined at 0. And we take in the mouse position, and we have the output behavior of that circle radius wormhole. So we're using this before it's defined. And then down here, when we define this, we can set what the input behavior is for the wormhole. So we just kind of solved this problem. And I'm not going to go into the details of how this whole function reactive program is done. But needless to say, we can do this mutual dependencies between behaviors that are defined in different places. And we also have this time shift property, because really when you ask it for its first value, when this one's defined before this one's defined, you need to figure out, if there's a mutual dependency, how to pull a value before the other one's been taken care of yet. So you just have this dt time shift. And that's also a really useful property. So if you want to write a behavior which does integration, you're going to use wormholes. So you have both of these, and there's no space leaks. There's no subtle time leaks. You don't have to put these special delays in your program. And this just follows directly because I derived this into C++. If you do this in Haskell, and you do a Haskell-based or a functional-based implementation of this, these are really common. But here, it just wasn't even an issue at all.
You haven't really talked about what they actually are, space and time leaks.
Okay, so the comment was that I haven't actually pointed out what they really are, space leaks and time leaks.
Brief example.
Okay. So an example of a kind of space leak that you might see in a Haskell implementation is if you have your function of time for a mouse position, for example. And let's say you want to take the integral of that thing. But you're not going to use that integral until like time 150. It'll build up, unless you are very careful about this, it'll build up the thunks to create that integral, and it won't evaluate it until you get to that time 150. So that's a huge memory problem. And similarly, it's you can get these time leaks issues where you ask it to evaluate something and it asks for something in the future and it just halts because you have the wrong dependency. So with these wormholes, you don't get these problems.
Is that an artifact of the laziness, essentially?
It is an artifact of the laziness, yeah. Okay. So another big problem with the Haskell things is integrating with imperative code. So let's talk about that. So this is where what you were asking about earlier, Eric, comes in. So you can create a behavior in a couple different ways. The first is a push. This means that you have a function that you call at some point in time, and every time you call it, it'll make a new event at that particular behavior. So we have this thing called trigger. You call trigger, and it returns a behavior of optional t and a function that you can call, which will make the behavior at the current point in time non-optional. It'll be that value. Does that make sense? So as this guy's writing, the behavior over here going like this, doing the trigger is basically like slapping him in the face, right? That's what a push-based behavior is like. You just, bam, give me an event at this point in time. Or we have pull-based behaviors, which means that whenever this behavior is being used, or conceptually you can just think about it as this function of time, and this isn't a pure function, this can be impure, it can get the mouse position, is going to create a behavior of that type. And we can just say that at the end of the day, you're going to be pulling these behaviors out. You're going to say, give me your value now. Give me your value now. Give me your value now. And with one of these pull-based behaviors, it'll call this function to give you the value at that time. Question?
So the thing I think I'm still confused about is the role of optional in this. I feel like I'm missing something you're talking about.
Okay, so
what role that's playing in this trigger?
Okay, so the question is, what is optional? How does optional play in this trigger? Does anybody know how? Does anybody else have an answer for that?
So I'm mapping this to concepts in Rx, this is like a subject. So you can ask the behavior optional t for any time t, and the optional only be returned true if you happen to hit the time t that a trigger was called for. So when you call the trigger function, it records the current time of value t, and if you ask the behavior for that time, you will get that t in the option.
Great. Thanks a lot.
Good answer. So the optional means that only at the time when that trigger occurs is that optional behavior going to be none.
So your little line over there isn't really a line at all. It's on the chalkboard.
So the comment is that
There's no value at the flat point of the line. There's no value at all.
So the comment is that on the chalkboard I didn't really do this right, and that's true, right? More accurately, these trigger behaviors are going to look like this.
It's called an impulse function.
And I have an infinitely thin finger.
What's the value at the bottom?
None.
Not zero or something. It's none.
Right. And this over here, these can be these can have a value. So this might be an int, which corresponds to the mouse button that was pressed at that moment in time. So this is how to create behaviors. And do you guys think that, how do you guys think about this interface? Would you consider this difficult to create behaviors from imperative code? Question.
My first instinct is that I'm going to have a polling problem if I can't sample at the exact time when trigger has a defined value.
So the comment is that you're going to have a polling problem if you don't sample at the exact time that you pull the value. And that's a good point. We'll talk about that in a second.
I'm not clear on how to use the trigger function. I don't understand that.
Okay.
But if I call trigger, it gives me back something.
So the trigger function gives you back a pair of things.
Back the behavior and the function that I need to call. Okay, get it. No.
Yeah. So it gives you back the behavior and the function that you need to call to feed it.
It might help a little bit if that was make underscore trigger, because it's actually a constructor.
So the comment is that it might help if it was make underscore trigger. I'll consider that.
So I think I see what you're doing here. So if I can use this interface, then I can reason about your system using control theory, basically, with impulse functions and everything I know about control theory. Is that right? The mathematics of it.
Yes, so the comment is that with this, using these functions, you can reason about your programs using control theory. And I'm not familiar with control theory, but it sounds similar. Yeah.
Right. You have triggers, you have impulse functions, and we have like PIV controllers, and we have a bunch of math that tells us what will happen.
Mm-hmm.
Right, exactly.
Was there another question? All right, so let's look at how we would pull a value out of our behavior. So we have our struct behavior, and our pull function is kind of weird because it has this precondition on it, which means that you can only call it with increasing values of time. If you call it with time t equals 1 and then call it with time t equals 0.5, you break the precondition. So that little trick there allows this whole thing to work. Because you're only pulling it at a given point in time, there's only one value for a given point in time. So the function is well defined, even though it might be doing imperative stuff. The fact that you can only call it with increasing values makes the whole thing work.
Is that a greater or a greater than? So can I call it twice at the same time?
So the question is, can you call it twice at the same time? And originally, I had it that you have to always call it with strictly increasing values. And so this is actually not accurate with the current version. You can call it with the same value in time. So you can ask, what is it at time 1, what is it at time 1, and then what is it at time 1.2? And that's fine. And that's actually important for when you want to have a behavior that's being used in multiple other behaviors that are defined in it. They both need to pull it and get the same value. So given this, what would your main loop look like? Anybody want to give it a shot?
I want to compose your control function and your impulse function with the natural function of your behavior, of what it is we're controlling, basically, and then that would give me the pull behavior that I want, basically. I know I'm not describing it.
Yeah, so the comment is that you would pull this thing, right, and you would presumably do something with it.
And I'm essentially integrating the composition of these two functions in time.
So the main loop in a drawing application could be, pull it at the current time, make sure that, we're not pulling it too quick, do a delay if necessary, grab the drawing and display it on the screen. So generally these things look like little loops where you loop over the time and you pull it and you do something with it. So how well would you say this interface maps to like C++ libraries out there? This isn't really a tough thing to use, I would argue. You set it up and it's not that hard. Just a few lines of code. So to try to sum up here, SFRP solved these problems that the Haskell implementation had on accident. It was just the fact that the semantics were being derived into C++ that none of these problems came in, which I think is pretty incredible, actually. We have also optimal and predictable consumption of space. The space is very well defined in terms of what kind of memory this thing is going to use every time you pull. Dynamic collection capabilities come automatically, really, because you can do mutability between time samples and it doesn't break your semantics at all. So the question is, what do I mean by dynamic collection? Imagine that we have a behavior of a vector or something like that. We don't have to make a copy of that vector every time we pull the behavior. We can instead have a pointer to a vector which is being updated, the mutability is being updated. So the dynamic idea is that these are changing in time, these collections. And that just works really well with C++ and these things. The implementation is really not hard. It seems like it would just be like some magic thing which is going on, but if you actually look at the implementation, it's just broken up into these basic steps. It's not using any kind of tricky stuff. And of course, we have it simple to use with imperative libraries. Comment.
I gotta ask, would it be possible to take your SFRP C++ library and map it back into Haskell?
So the question is, can we map the SFRP library back into Haskell? And yes, it would be possible. Question.
What does the S stand for in SFRP?
Nothing. I put an S before all my libraries. It just stands for S. Question back there.
So in this case, fundamentally, we were using time to get the mouse position. We're incrementing forward, but couldn't fundamentally we drop time out? If we just assume current time, the main loop is something like, a 60 hertz pulse, where we pull at 60 hertz. Do we even need time?
So the question is, do we even need time? And I think the answer to that is probably no. You could probably get away with not having time. You could do a time as a behavior which is defined using trigger.
You can sample time once for every calculation. Otherwise, different parts of the calculation are going to be sampling time in a bunch of different places. And if it's a long-running computation, you could imagine different parts of the computation getting different results for the current time.
You also don't want to call current time one. Slow time.
Well, I mean, the way the library is done, if you ask for, it would have to be a different kind of library, right? Because you're not asking for things at a certain time. Yeah. Question?
So an additional reason to keep time as a variable, although that Eric's is perfect as well, is testability. Being able to forward time faster than real time.
So a comment is testability is another good reason to keep time involved in this thing. And that's actually been useful.
Yeah, another piece of time is it allows you to interpolate. It also allows you to have predictive behaviors. So if you want to start rendering something during an animation so that the rendering is done by the time the animation completes, then you can predictive behaviors that are fed with a clock that's in advance of now. So you extrapolate.
Yeah, common is time extrapolation, all that stuff. And you can, in this library, we do have things like integration and all that built up using these primitives. So I want to go back really quickly. Oh, go ahead, question.
Yesterday we saw, the other briefing and talked about performance. Have you checked any of your performance with using?
So the question is, have I done any performance tests? And the answer is no, but I know that it's really fast. There's not like pointers and stuff going on. It's straightforward every frame. Another question down here?
One last question about time, and one thing I still didn't quite get is, so since we are always pulling the current time, and how would I implement something where I need the velocity? I don't know, I want to throw the ball kind of thing. I want to kick that thing, and then I need the current time, the time before. Where does the memory come into?
So the question is, how would you implement something where you need, like, where you want to implement velocity? Or, like calculating the derivative of something or something like that. So that wormhole, that time shift property, that dt thing, you can use that to implement all that stuff. Question over
Do you
here.
have that library open source somewhere, and if yes, which license does it have?
So the question is this library open source, and what license does it have? The answer is, of course, it's open source. And the license is, I actually didn't upload a license file, so what license should it have?
BSD?
BSD, that's fine. Boost. What? How about a dual license? I don't know.
Boost is equivalent, pretty much.
Okay, I'll put it Boost because this used to be BoostCon. Go ahead.
So one performance-related question. So basically, in the outer loop, I'm pulling, and then a bunch of functions does something. But that might take a long time depending on all the conditions. If I want to sort of have a smooth transition, if I want to drop frames if something takes too long, I can only do that after the fact. So it's something like I put in a time t, then I recognize, okay, that took too long. Then I, of course, can adapt the time stuff, but that's after the fact. Did I get it correctly?
So the comment is, did I get it correctly? So all of these problems would happen in the puller, right? And there are certain things that you can do to kind of mitigate these things. But generally speaking, unless you're calling some kind of crazy mathematical function, this is just ridiculously fast.
So what is the most complex program that you have implemented using this?
So the question is, what's the most complex program I've implemented using this? And I will get to that in a minute, yeah.
I want to ask more or less the opposite of his question. It looks like the central loop is going to run hot. It's just constantly polling. Is there a way to have it, to have it go to sleep until the next thing needs to be done? Or does it have to have what it needs there to just pick a time in the future to do the next thing?
So the question is, well, the comment is that this runs in a really hot loop. It seems like there should be some way to figure out if there's new stuff to do. And the answer to that is, in practical cases, I don't ever run this hot, right? There's only a certain frame rate that I need for these animations, for example. Yeah.
Yeah, but if it's a dot on the screen that never moves, you're still running at 60 frames per second.
Yeah.
Like you have nothing in the system to say, you know what, don't even call me again because, I know nothing's changing or whatever. Like I don't know how you would do it, but that's the question.
Okay, so yeah, so if we do have something centered on the screen, ideally, you would like it to know that it's never going to change, just have it completely dead CPU, no
It
polling.
doesn't change until it triggers.
Or it doesn't, so yeah, or a trigger function or something does that. So this library doesn't have that capability. That's an open problem. Question down here.
So this is what all this push-pull reactive programming was about, that you don't want to be constantly pulling. You want to have also a push model in which events, you were talking only about behaviors, but there's also something called events.
Mm-hmm.
Events are just these discrete things that arrive at you and force you to do something rather than you polling.
Yes, so the comment was brought up that push-pull programming solves exactly this kind of issue, or aims to solve this kind of issue. And this has the same semantics as that. So push-pull programming with Connell's latest library, the one that I was working on, you can implement that with this, because it's just a matter of when you pull, for example, one of these behaviors, it just waits until something's ready. So that kind of thing can be implemented in this, but I haven't messed with it because all of my applications have been continuous based stuff. Yeah, question?
So forget dots and screens. I mean, you can implement like a robot arm grabbing this glass and picking it up, because you have a model and you don't have to sit there like we used to in the old days, basically monitoring it all the time. This is amazing.
Yes.
Where were you 20 years ago?
So the comment is that you can use this for a robot. It's not limited to dots on a screen. And actually, dots on the screen, I just did this to demonstrate this. That wasn't my application at all. Let's go over here. There's a question back here. No? A question?
Can you drive this entire model with space instead of time? So, for example, points on a 2D plane. If you have some notion of non-decreasing space. I mean, I wonder if there's a general concept that can be factored and so to make this applicable not only to the time domain.
So the question is, can this be applicable to something different than time, like, for example, a space domain? And my initial thought is that time is kind of integral in the semantics of this thing. And the specific nature of time is always increasing is an important part of it. So I'm not sure how it would apply offhand.
Can you explain a bit how the push model actually makes it, if your main loop is pulling, how does that trigger at that infinitesimal time t get samples in your main loop?
Yes, back to Zach's question. All right. So the key is, and this is why the semantics of this are still sound. Imagine that we have another behavior like this. And it has values. And each of these values corresponds to when a pull was done on the resulting behavior. So if we have something that happens over here, the way I define it in the program is, let's say the actual event happened here. And the trigger function is like, bam. I want to make sure that I pick it up at the next pull. So I define this to actually be the same value until I get that pull.
You integrate it.
So I'm guaranteed with these triggers to always, retrieve them. Yeah. And one of the common complaints of these functional programming libraries in the Haskell community is that they break the semantics when they deal with these kinds of things. And the introduction of this idea of the pull event is what makes this whole thing sound and makes it be mathematically correct. Although that might not be that important in terms of implementation purposes. Question?
What happens if you need to carry some sort of state through time? Changes.
So the question is, what happens if you need to carry some kind of changing state through time? So you can just do that, right? That is sort of what this is as a whole.
You wouldn't need the history.
Comment is you wouldn't need the history, right? You wouldn't need the history unless you specifically need it to define your future in terms of the history, in which case that works too. Zach?
So is the trigger function step, or do you make a hole at the first time you pull from it?
Well, actually, this is the conceptual model, but you could just as easily say that I'm moving this event over to here, and it doesn't actually exist. Because I don't actually pull at that point in time, it doesn't matter what we want to imagine it to be.
What happens if you pull it in before the next event?
What if you sample too many times?
Oh, okay. So in that case, you don't get more than one. Yeah. Question down here?
So I want to ask the opposite question. If you sample too few times and you get multiple triggers in between samples, then you're going to lose some unless you have a way of queuing them, which is typically done in UI programs.
So the comment is if you have too many events happen between these things, then you're going to lose some. And you could make a mechanism to, clump these together.
Yes,
Yeah.
I was going to say we've got three basic mechanisms that we define. One is give me current. One is guaranteed forward progress, which is to say that since these things can take time to evaluate, that while you're evaluating one and the other one's coming, you don't cancel
granted forward progress, we have give me every one and give me current one.
So we had a comment of how what the conceptual models are, or implementation models are, that are used at Adobe. Yeah.
So your driving function doesn't have to be a impulse function. It could be a function, and then you can use your lazy mechanisms to integrate between the times when the driving function is active and apply it, essentially integrate it too, and then exhibit more complicated control behaviors, basically, right? I mean,
Yep.
it essentially scales with the mathematics.
Yep, so the comment is that it scales with the mathematics because we have the continuous functions, and that's true. Is there a question?
So a lot of this can be understood if you know a little bit of digital signal processing. So this is an impulse function. What you're doing with this, you are integrating it. So like every impulse is setting a latch, right? And then you have another behavior, which is the probing behavior, and every time you probe, you reset the latch. Right, so you subtract it back to 0.
Okay.
And so on. So you can accumulate events, and then you can reset them.
Okay.
So,
Interesting. So there was an explanation as to how this directly relates to impulse functions, and I'll definitely have to look that up. All right. Oh, another
Okay,
question.
just real quick,
Sure.
the diagrams you're drawing in Reactive Extensions, the .NET version of this with monads and some other things, they call them marble diagrams. I mean, there's all sorts of things to help people understand what's going on. So you look that up too.
Yeah, there's comments that, there's a lot of diagrams out there that can be used to explain this, and that's true, yeah. All right. So that's an introduction to SFRP. Now, SFRP is not a one-off job. This is an industrial strength library. This was designed for Sandia National Labs for a 6-axis layered manufacturing robot. I developed this CAD-CAM tool, and this was the way that we got this robot to move. It was extremely complex. We had to have real-time inverse kinematics going on. There are limited motion ranges that we needed to take in consideration. Some of the speeds of these motors, couldn't go beyond a certain point, so you needed to deal with that kind of a situation. There was, this conformal accuracy, and you'd want positional accuracy to be more important than the conformal piece, based on the limitations of your motors. The real-time adjustments of the path during the build. Let me just say, this was one complex interactive issue. And yeah, this is a big project. So this really, I think, proved the concept. This isn't just a toy. This was used for a real project. Big one. So the end result is that all of these requirements were met. The SFRP specific code was around 2,500 lines. If this was written in a normal imperative style, I honestly don't think we could have done it. I mean, it would have taken a lot of time and certainly a lot more code. Each Qt widget that you see here in this screen had corresponding behaviors to it. So we were able to take our normal Qt widgets, and now they're behaviors, and now we can use these in our formulation for everything. And it was certainly a challenge, even with SFRP. But it all worked, and it was very straightforward stuff. So just to give you an example of the kind of things that happened with this project, we had a surprise requirement that they wanted this complex, conformal printing thing. They wanted to be able to nudge it so it's off a little bit like this, because whatever the conformal printing was going on, they needed it to be off a little bit. And this adjustment happens during the build. So you need this to move out and then stay that distance away from your object the entire time that it's building. And this feature was added in less than a day. I just needed to go in and find the behavior that controlled the actual driver of the thing, the physics, and say that, okay, the distance, that this tip here is now a little bit shorter or a little bit longer. And I could just use these smooth integration functions, and it would just gently make that motion and do the whole thing. A very, very complex thing to think about, all these different, if you try to think of all the pieces that have to move at the same time, it's just mind-boggling. But when you're in this behavior world, it's direct, right? You only have this little context that you're thinking about, and you just make this adjustment. You have these smooth functions that you can reuse, and it all just fits together. So yeah, we just added this new behavior, connected it to a widget, and we were done. So that was a big deal. That surprised even me how quickly we were able to add that feature. So that is SFRP in use. The question is, when would you want to use this thing? You could use it in robotics. You can use it in computer animation. You can write games with this. Anything interactive, really. Anytime there's any kind of interactivity with time, this is applicable.
I'd like to make the point that nearly every app these days is a computer animation thing that's dealing with events.
So the comment is that nearly every app these days is computer interaction with events. And I don't know if that's true, but there's certainly a lot of those. Yeah. So the benefits of using this. We have an old way of doing this. Why would we want to use SFRP? Cleanly abstracted. We got the right semantic domain. We got the right mental model. It makes so many things possible. This is practical, right? If I tell you there's a fantastic, Haskell library that you can use for doing this kind of stuff, most people in this room would just be like, forget it, because that's just not practical. This is in C++, extremely practical. And these things are composable. It's like Legos. How many computer programmers don't like Legos, right? Legos are awesome. And that's what this feels like. You just hit these things together and it works. So there's a lot more to learn about this. I didn't even talk about events. And this is behaviors with specific occurrences. And there's a lot of different ways that you can, take an event and based on the event, sample the behavior at those particular times or, change everything. I'm not even going to get into that. There's behaviors of behaviors, which is an interesting concept that comes up every once in a while. And integration, derivatives, all this kind of stuff can be done with this library. So when I originally wrote this, I thought that it was pretty solid, good industrial strength code. And that was until I saw the source code to BDE by John Lakos. And that code is the most amazing practical code I've ever seen in terms of documentation and examples and all that kind of stuff. So I have made this like that. This is following the BDE coding standards to a very large extent. So if you clone this repository in particular, this SBase, you'll be able to go into the headers and see extensive documentation, examples, why we want to use this. It's all there. And I think that is the end of my slide. So does anybody have any comments or questions at this point?
I would like to comment that this FRP solves another problem. It's like basic problem of programming, let's say in Windows, GUI applications, the inversion of control. That you always write this loop of control, right, and you are waiting for events to come, and then you are reacting to them, and you have the problem of keeping state around. You usually use global variables for state, awful things like these. This completely reverses this. You are no longer reacting to stuff. You are planning stuff ahead.
So the comment is that with this change in paradigm, you're no longer reacting to stuff. You're not reacting to like this event happening and maintaining state beforehand. You're actually planning for things to happen. And maybe it should have been called planning reactive programming or reactive functional planning programming. Go ahead.
So this model uses time as a basis, and time goes on forever. Is there a particular pattern for dealing with things which have lifetimes, like get created at time t and destroyed at time t plus k?
So the question is, does this handle the idea of of a time that sort of expires, like this thing expires? And the answer is yes. So that the semantics for this thing. So I derived the semantics into the implementation in behavior.hpp. That's one of the sections of the documentation. And I explicitly handle that case. We didn't talk about that here just because I wanted to simplify it for this, for the context of this talk. But that is integral into the semantics that, yeah.
Like you can just take an object or a behavior out and delete it and throw it away. And now it no longer exists.
So the comment is that you can just take a behavior out of the way, delete it, and it no longer exists. And it's not straightforward like that. Yeah. All right. Well, that's it.